Okay, well, we're about to move into our next unit, Unit 3, and Unit 3 is about compounds. And so I am going to start the unit by giving you a discussion of ions, which are charged atoms. And so we're going to start by talking about what I call noble gas wannabes, which is that all atoms want to be like noble gases. And then we're going to talk about types of bonding really briefly. Then I will talk about common ions, that is how elements typically gain or lose electrons to become ions. And then we'll briefly talk about polyatomic ions, which I will describe in a little bit more detail in just a moment. So let's talk about noble gas wannabes. So I kind of came up with that term. Basically, what I'm trying to say when I say noble gas wannabes is that more or less every element on the periodic table wants to be like the nearest noble gas. And we'll talk about that, the why of that, in a little bit more detail later on. Well, we've talked about the fact that in chemistry you can't convert an atom of one element into an atom of another element. And so it's not possible for atoms to actually change themselves into noble gases. So really the best they can do is to have the same number of electrons as the nearest noble gas. And so we're going to spend a lot of time in this video talking about how atoms gain or lose electrons to have the same number of electrons as the nearest noble gas. And so let's just sort of look at a periodic table and say what we're talking about. So let's take, for example, bromine. Bromine, element 35, its nearest noble gas is krypton, element 36. And so bromine is going to tend to want to gain one electron so that it will have the same number of electrons as krypton. If we think about oxygen, here, element 8, its nearest noble gas is neon, element 10, and so oxygen is going to tend to want to gain 2 electrons so that it can be like neon. If we look over at the other side of the periodic table, let's say, for example, strontium. Strontium is element 38. Its nearest noble gas is not xenon over here in the same period. Its nearest noble gas is actually krypton. You'll notice that strontium is element 38, krypton is element 36. And so strontium, rather than gaining electrons, is going to want to lose 2 electrons to become like krypton. If we look at sodium, sodium here is element 11. Its nearest noble gas is not argon, element 18, but neon, element 10. And so sodium is going to tend to want to lose 1 electron to be like neon. We're going to focus in this video almost entirely on what are called the main group elements, elements in groups 1, 2, and then 13 through 18 or 3A through 8A. We're not going to say much about transition metals in this video. Okay, so metals tend to imitate the nearest noble gas by losing electrons, and therefore they become positively charged, and a positively charged particle is known as a cation. Nonmetals, and the examples we gave were bromine and oxygen, tend to imitate the nearest noble gas by gaining electrons and therefore becoming negatively charged, and we call a negatively charged particle an anion. Nonmetals can also imitate the nearest noble gas by sharing electrons with other nonmetals, and when that happens, that's called covalent bonding, which we'll talk about just briefly in this video, but we will discuss in greater detail later on. So that leads to 2 types of compounds. You can have either ionic compounds in which you have a positively charged ion and a negatively charged ion coming together to bond. Or you can have what are called covalent or molecular compounds in which you have small units or collection of atoms held together by covalent bonds. And so the simplest way to think about this is, well, let me first just talk about what does an ionic compound look like? An ionic compound is a crystal lattice like this. This is sort of a cartoon version of sodium chloride. The sodium ion is positively charged, the chloride ion is negatively charged, and they just form this giant crystal lattice of alternating sodium and chlorine atoms. A covalent or molecular compound is different. You're going to have atoms sharing electrons to form a small unit like this called a molecule. And that's an example of a water molecule. It's fairly simple in looking at the formula of a compound to determine whether or not it is ionic or covalent, or in other words, whether it is ionic or whether it is covalent. And the simplest guideline for this, I would say, in our course this year is going to be if the formula contains a metal, if a compound contains a metal in its formula, then that's pretty much an indicator that it's an ionic compound. Whereas if the formula consists entirely of nonmetals, that's going to be a covalent or molecular compound. So we can go through a few examples and just talk about, I'll show you an example and you can tell me what kind of compound it is. First example would be KBr, potassium bromide, because it contains potassium, element K, which is a metal, then that's an ionic compound. Sodium sulfate, Na2SO4. You'll see that formula contains sodium, Na. Sodium is a metal, therefore that's an ionic compound. Hydrogen chloride consists of hydrogen and chlorine. Both of them are nonmetals, therefore hydrogen chloride is a covalent compound. P2O5, it contains phosphorus and oxygen. Both phosphorus and oxygen are nonmetals, so that's a covalent compound. AlCl3, aluminum chloride, that contains aluminum in its formula, therefore it's ionic. Glucose, which we've talked about recently in some of our exercises, contains carbon, hydrogen, and oxygen. Those are all nonmetals, so it's covalent. Carbon dioxide contains carbon and oxygen, which are nonmetals, so it's covalent. Silver nitrate, AgNO3, contains silver, that's Ag, so that is an ionic compound. Copper 2 oxide contains copper, that's Cu, so that's an ionic compound, that's a metal. So that copper oxide is an ionic compound. NH3, ammonia, consists of nitrogen and hydrogen. Those are both nonmetals, so ammonia is a covalent compound. Just as a reminder as where we find metals and nonmetals on the periodic table, the metals are going to be everything to the southwest of this red line that I've drawn here. So everything in here, groups 1 and 2 excluding hydrogen, all the transition metals, all of the inner transition metals, and then some metals down here like tin and lead. These are all metals. Everything to the upper right, the northeast of this line, plus hydrogen, is a nonmetal. The most common ones we'll deal with in this course are going to be hydrogen, carbon, nitrogen, oxygen, the halogens, fluorine, chlorine, bromine, and iodine, phosphorus, and sulfur. These, as you'll recall, these sort of dark shaded elements along the stair step here are called metalloids, and it will not be very frequently that we will be talking about metalloids. Okay, so an ion, as I mentioned earlier, well, maybe I didn't mention earlier, but I simply said a positively charged atom is called a cation, and a negatively charged atom is called an anion. But an ion is an atom that has an unequal number of protons and electrons. It's essentially a charged particle. And so that's going to happen when an atom gains an electron or loses an electron, or it could gain 2 or lose 2, or even as many as 3. And that's going to form an ion. And so as we were talking, so metals are going to tend to lose electrons. And as I was going through the periodic table earlier, showing you that things like sodium and calcium are going to tend to lose electrons to become like the nearest noble gas, and so they form cations. Nonmetals, and the examples we looked at were bromine and oxygen, tend to gain electrons to form negatively charged ions, and we call those negatively charged ions anions. So let's just do a quick little practice routine. This is going to be based on thinking about looking at a formula for a cation or an anion, looking at what the charge is and figuring out how many electrons were either gained or lost to form that cation or anion. So this is the barium cation. It has a charge of +2. This is the arsenide anion. It has a charge of -3. This is the copper-2 cation. It has a charge of +2. So if you'd like, you can just pause the video, take a look at these, and ask yourself, how many electrons were gained or lost to form these ions? Well, the key to this is always remembering that electrons are negatively charged. And so if a substance has a positive, if an ion has a positive charge, that means it has fewer electrons than protons, and therefore it lost electrons. So the barium 2, the barium cation, having a charge of +2, got there by losing 2 electrons. What's called the arsenide anion, which is formed from arsenic, which has a charge of -3. It therefore has 3 extra electrons, and therefore it had gained 3 electrons. And then copper-2, having a charge of +2, is a cation, and it got there from copper by losing 2 electrons. We're not going to spend a lot of time talking about this, but I just wanted to bring it up briefly. The formulas for ionic compounds is the lowest whole number ratio of ions in the compound. As you'll recall from the picture I showed you of sodium chloride before, um, individual ions are not bonded to other individual ions in molecules. Rather, they have this large extended array type structure. And so when we say that this is sodium chloride, NaCl, we are giving as you'll recall, the empirical formula. So the empirical formula for sodium chloride is simply the lowest whole number ratio in which sodium and chlorine atoms combine, and that's in a 1-to-1 ratio. And so sodium chloride, we give simply the formula of NaCl. That's the empirical formula for this crystal. This is a picture of the crystal of magnesium chloride. It's a little bit harder to see this. It's not in sort of a nice extended uh, image like this where it's clear to see that these are in a 1-to-1 ratio. But magnesium chloride is also a large extended crystal lattice like this. And the magnesium and the chlorine ions are there in a ratio of 1-to-2. And so no matter how large and big and extensive that crystal lattice is, we simply say MgCl2 because that's the ratio in which they exist in that compound. So let's just talk about what I would say ionization trends. And the simplest thing to take home from this is to understand that for the main group elements, that is groups 1 and 2, and groups, depending on which numbering system you're using, 3A through 8A or 13 through 18, the group number is going to tell you what the charge of the ion is going to be. So all these alkali metals, because because their atomic number is 1 more than the previous noble gas, they are all going to lose 1 electron to be like the previous noble gas, and therefore they're going to have a charge of +1. All of the alkaline earth metals, because they have atomic numbers that are 2 higher than the previous noble gas. So, for example, magnesium is element 12, neon is element 10. Magnesium wants to be like neon, and so it loses 2 electrons so that it can have the same number of electrons as neon. And so you'll notice that all the group 2, all the alkaline earth metal elements have charges of +2 when they ionize. If we look over here at the nonmetals and we look at group 7 or 17, which is the halogens, you'll notice that they all have atomic numbers that are 1 less than the nearest noble gas, and therefore they're going to gain 1 electron to be like the nearest noble gas. And so you can see that all the halogens have charges when they ionize of -1. And we can work through the same reasoning as to why things in group 6A or 16 ionize to form charges of -2, and why things in group 5A or group 15 gain 3 electrons to be like their nearest noble gas and have charges of -3. The important thing to notice about this chart is that the noble gases don't ionize, and the reason is because they are the nearest noble gas. They already have the same number of electrons. I mean, they already have the number of electrons that they want, and so they never ionize. We will not talk at this point anymore at all in this video about the transition metals, which you'll notice that some of the transition metals have more than one ion that they form. So we won't concern ourselves with that right now. Instead, let's do based on what we were just talking about, let's do a little practice exercise here. So using only a periodic table as your guide, and what I mean by that is don't go back to the previous slide in this presentation. Predict the ion that'll form from each element that I've shown below. So if you like, you can turn the video off for just a moment, write this down, and then turn it back on. Okay, well, lithium is in group 1. We mentioned that everything in group 1 wants to lose 1 electron to be like the nearest noble gas. Lithium is element 3, and so it wants to lose 1 electron to be like helium, and therefore it'll have a charge of +1. Bromine is in group 7, and so therefore it is 1 electron, it is 1 atomic number shy of the nearest noble gas, and so it's going to want to gain 1 electron to do that, and so it's going to have a charge of -1. Calcium, element 20, its nearest noble gas is argon, which is element 18, and so it's going to want to lose 2 electrons to be like argon, and therefore it is going to have a charge of +2. And then phosphorus, which is element 15, is its closest nearest noble gas is also argon, which is element 18, and therefore it's going to gain 3 electrons to be like argon and have a charge of -3. All right, the last thing we want to talk about, and I'm not going to put a lot of time into this in this video, just to let you know this is something coming down the pike, which is what are called polyatomic ions. There are certain ions that consist of more than 1 atom. And so all the ions we've been talking about up till now are just a single atom that has a different number of electrons than it does protons, and therefore it has either a positive or a negative charge. But you can also have what are called polyatomic ions, which are essentially like molecules, covalent molecules that have acquired charges. We're going to use, over the course of the year, we're going to use the polyatomic ions often in this course. So it's important for you to be able to recognize them, know their charges, and not have to be constantly looking them up. And the thing about the polyatomic ions is there's really not a good way of memorizing what their charges would be based on using a systematic way based on the periodic table. You simply have to memorize these things. And so these are the 10 polyatomic ions whose formulas and charges you're going to need to have memorized. At some point in this unit, I am going to give a quiz on this. And so there is a handout for you today, which is a list of these 10 polyatomic ions with their names, their formulas, and their charges. Once again, you'll see that these look a lot like covalent molecules in that they are made up entirely of nonmetals, but then they have a charge attached to them. And so you'll just want to start working your way through that handout and memorizing these 10 polyatomic ions, their names, their formulas, and their charges. Okay, well, thanks so much for watching the video. There is a worksheet, in addition to the polyatomic ions handout, there is a worksheet for you to do. So you can go ahead and get the worksheet and complete it, and that will be your assignment for today. Thanks so much.